6.3c, calculate the mean and standard deviation of a binomial random variable and interpret it in context. So if you're asked to find the mean of it, it's not difficult, and this is on the AP formula sheet. So to find the mean, all you do is you take n times p. To find the standard deviation, we take the square root of n times p times 1 minus p, where n is the number of trials and p is the fixed probability of success. So we're back to the rolling doubles example, folks. X is the number of doubles in 4 attempts. Again, we have n is 4, p is 1/6. We have the probability distribution here to our right. They want us to find the mean, the variance, and standard deviation. So to find the mean, be cautious. We do have a probability distribution here. Don't forget how to find the probability distributions mean. Just take the outcome times probability and you add them all up together. So for this one, we're going to have what we did before. The mean is going to be, on average, we're going to have 0.667 times doubles will be rolled. Well, that obviously is theoretical because it doesn't make sense. Now, be careful. That's not the only way to do this one. I can do it from the distribution, but because it is binomial, and I know that, I could use the new formula. So what's kind of clever is I could do n times p. So 4 times 1/6 is 2/3. You get the same answer, and they're both correctly done. Now, to find the variance for this one, let's go ahead and just talk about what we did before. Remember, we did our variance of a distribution. We can go ahead and do this, right? We're going to take each piece of data minus the mean, square it times the probability, add it up. So standard variance on this is going to be 0.556. To find the standard deviation, we're just going to come on in and we are actually going to take the square root of that and we get our standard deviation at this. Now again, because it's binomial, I have a second option. I could come on in and use this formula. It's clever how it works. N is 4, probability of success is 1/6, failure is 5/6, take the square root, and we have the same answer. Now the Diet Coke example, we're kind of switching gears finally. The makers of Diet Coke claim that its taste is indistinguishable from a full calorie version of the same cola. To investigate this, AP Stats students prepared small samples of each type of soda in identical cups, then had volunteers take each cola in a random order to identify which was the diet and which was the regular. Overall, 23 out of 30 made the correct identification. So if we assume that the volunteers really couldn't tell the difference, then each one was guessing at a 50-50 or 1/2 chance. Okay? Let our variable be the number of volunteers who correctly identified the colas. Explain why X is considered to be a binomial variable. Okay, let's go through bins. Well, bins would say binary. Yes, either guesses are correct or incorrect, success or failure, so that meets binary. Are they independent? Sure, each student's independent from each other in the class. One volunteer should not affect the other. Was there a fixed number of trials? Yeah, there were 30. 30 students did this. And was the probability of success the same for each? Absolutely. The probability of success was always 50%. X is a counting number of successes, and therefore X is considered a binomial random variable because it meets bins and it deals with counting. Well, since we know that, we could go ahead and actually compute the mean and standard deviation. And let's use the new formula because it is binomial. The new mean is just n times p, so 30 times 0.5 means we would expect 15 students to guess correctly. Standard deviation, let's just do that one. Square root of n times p times 1 minus n times p. Standard deviation is 2.74. So what that's going to tell us is that if this experiment were repeated many times and the volunteers were randomly guessing, the average number of correct guesses would be about 15, and the number of correct guesses would vary from 15 by about 2.74 on average, is how would we explain these two in context. Part C, of the 30 volunteers, 23 made correct identifications. Does this give convincing evidence that the volunteers can actually taste the difference between diet and regular cola? Well, if 23 made the case, what if we found the probability that 23 or even more than that actually could tell? That would be extreme. So what I'm trying to do is let's find the probability that x is greater than or equal to 23. Okay, we've already talked about bins, so let me just identify the parameters. We know it's binomial distribution. N is 30, P is 0.5. Well, how do you compute the binomial probability for this? We have to be careful. Remember, our calculator, if we use that, doesn't go forward, it goes backwards. So we can't do it at 23. So really, since it's discrete, we have to go from 22 on down. Let's find the binomial CDF of 22 on down, subtract it from the whole, and we got it. So I'm going to write this. 1 minus the probability of x is less than or equal to 22. So I would type in my calculator 1 minus the binomial CDF of this scenario. If you do that, you're going to get 0.0026 is the answer. So 0.26% chance, which means there's a very small chance there would be 23 or more correct guesses if the volunteers couldn't tell the difference in the COLAs. Therefore, we have convincing evidence that the volunteers can actually taste the difference, and we would disagree with the company. Again, do note you could have done this probability a different way. You could have done binomial PDF for 23, 24, 25, 26, 27, 28, 29, and 30 and added them up, which would have also been sufficient. This is by far a more efficient way of doing the problem, though. Now, there's one thing we have to start introducing is what if we are doing sampling without replacement? We noticed earlier if you sample and you don't replace and you do the next trial and you don't replace, you violate independence because you've changed your sample size. Well, in statistics, we actually hit this without replacement condition a handful of times. And we want to address, is there a way we can get around it? And there is. From now on, you're going to be used to the 10% condition. And here's what it says. When taking an SRS, simple random sample, of size n, from a population of size capital N, we can use a binomial distribution to model the count of successes as long as this condition is met. So there's two ways to look at this condition. If they're not replacing, you can still do binomial as long as your sample size is less than or equal to 1/10 of the population. Now, personally, I like to move this over. I like to multiply both sides by 10, and I like to use this formula. I reference this one. They're the same thing. But if you rewrite it, what it would say, your population, because that's capital N, must be greater than or equal to 10 times your sample. If you meet this requirement, it is called meeting the 10% condition. If you meet that 10% condition, even though independence is violated because you didn't replace, you can still use this probability method. So, in conclusion, you can ignore the lack of independence when a sample is less than 10% of the population, which is this, or if the population is greater than 10 times the sample. So again, these are the same thing. If they're met, you can ignore the replacement and you can use it. Thing to keep in mind, we don't want small samples, right? We don't want to have small samples, so you have to be really thoughtful in this, is that if the condition is not met, you cannot use the binomial distribution. So if there's no replacement going on and this condition isn't met, you have to scrap it and do something else. So in here, let's look at some dead batteries. Almost everyone has one, a drawer that holds miscellaneous batteries of all sizes. I know I do at home. Suppose that your drawer contains 8 AAA batteries, but only 6 of them are good. You need to choose 4 for your graphing calculator. If you randomly select 4 batteries, what's the probability that all 4 batteries you choose are going to work? Well, why is this answer they're saying we want to do a binomial that x equals exactly 4 work, right? So they're going to say, I need 4 and I choose 4. They're doing this probability. Probability of success, they're saying, is 6 out of 8. So failure is 0.25. And they're saying this is the answer. The actual probability is this. Why doesn't this work? Well, we've got an issue. Here they are sampling without replacement. Because imagine these batteries are in a drawer. You pick out the first battery, you're not going to put it back in there. You're going to keep drawing. You've done without replacement. So you want to be really cognizant of that. The selections aren't independent. So now, can you use binomial? You have to check that 10% condition. So if you go back to the concept of the 10% condition, ignore the problem if the population is greater than 10 times the sample. Okay, well, is it? Well, my population is 8. My sample is 4, so is 8 greater than 4 times 10? Clearly, 8 is not greater than 40. This does not hold. Keep in mind, we also could have looked at it as being, is our sample of 4 less than 1/10 of our population of 8? Well, if you do that, is 4 less than, there's going to be 0.8. Clearly that doesn't hold. So I just looked at the condition 2 different ways, either on the greater end or the less than. So in this case, what we have to do is conclude that we have to ignore if the sample is less than 10% of the population. 4 is not less than that, so it's not reasonable for us to ignore the lack of independence and use binomial. We can't do that in this case. I do want to briefly talk about what's called the normal approximation for binomial distribution. This is not required for the AP exam, however, it can be fairly common in statistics to use. And what it is this. You can actually use the normal CDF, where you do lower bound, upper bound, mean and standard deviation. For a binomial distribution, what you would first do is compute the new mean, compute the new standard deviation. That's what you're going to use in the normal CDF. But what you first have to do, if you do this, you must check that this condition meets. Is the sample size times the probability of success greater than or equal to 10? And is the sample size times 1 minus that probability, which is basically the failure, greater than or equal to 10? If it is, again, you can use normal CDF. Now, it is an approximation. So if you're looking for the most accurate answer, binomial is going to give it to you. But if you want to get a fairly decent answer, you can use normal approximation. And the AP board will actually take that if it's done properly, and this condition here is actually checked. Let's actually go back to that Diet Coke example. Remember, that gal did an experiment and 23 of the 30 volunteers could tell the difference. What if I wanted to do the normal approximation of the binomial distribution instead? I could, and here's how I would do it. I'd first check the conditions. You must show n times p and n times 1 minus p, and you have to put some numbers to it. So in this case, our n was 30, probability of success was 50%, so 15 is greater than 10 is great. Here, 15 is greater than 10 is great. So then I do need to find the mean and standard deviation. So I'm going to go through, use our formula for binomial. This is on the formula sheet if you forget. I'm going to show a little bit of work for that. So here we have our mean and standard deviation. And then you literally just do normal CDF. So you would type normal CDF. Our lower bound is going to be from 23 up to 30, the new mean and standard deviation, and here's what we got. If you compare that to what we got with binomial, we actually got this answer. Binomial is the most accurate, but again, if you check your condition, the AP board is going to be okay with this approximation. Let's do one last example, teens and debit cards. In a survey of 506 teenagers ages 14 to 18, subjects were asked a variety of questions about personal finance. One question asked is if they had a debit card. Suppose exactly 10% of those teens said they have a debit card. Our sample size is 506, by the way. We're going to have the event X stand for the number of teens in our random sample that actually have the debit card. Okay, is this binomial? So I need to show that bins actually does work. So if you check it, is it binary? You either have a debit card or you don't. Is it independent? Is there any independence between this scenario? I will tell you the independence on this one gets questioned. They will say, if you're teenagers in this group having a debit card, it may not be an independent event. So in this case, they're going to say, no, it's not independent, but let's check the 10% condition. Again, I personally am going to use the population. Is it greater than 10 times the sample size? And this is where it gets somewhat general. They're going to say here, yes, the population is going to be greater than 5,000 and 60 students. We don't know at this school, but we would just say, yes, we're going to assume the 10% condition is met as long as the population at the school has at least 5,060 students. And the population is millions of kids. There's millions of teenagers from 14 to 16. Okay, so I can choose in this case to do the normal approximation. So let's check the conditions for that. Do n times p and n times 1 minus p. So n are going to be 506. Probability of success is 10%. Here I get 50.6, greater than 10. Here I'm going to get a probability of failure is 0.9. It's definitely greater than 10. So I can do a normal approximation. So let's look at the question. They want us to use the normal distribution on this one just to kind of practice it. To estimate the probability that 40 or fewer teens in the sample have debit cards. So 40 or fewer, so the probability, what I would write is I'm looking for the probability that x is less than or equal to 40. I'm going to do normal CDF, my lower bound and upper bound. This is the mean for binomial. This is the standard deviation for binomial. And that'll give me an approximate answer right here. Now, what if I want a more accurate answer? If I did the binomial distribution with that, you could do binomial CDF. We have 506 in our sample, 10% success, and I want to know, in this case, 40 or less, so I would do CDF, and we would get this answer. Now, I'm a little hesitant to actually show this one because the independence wasn't met. Remember, this 10% condition allows me to use the normal approximation. It doesn't really allow me to use the binomial necessarily for that. But if it was truly binomial, that would be the exact answer. So in this case, the 0.058 is better because I'm kind of cheating halfway by using this condition, which only, again, applies for normal approximation.